I was asked to make a screencast going through the algebra of the dynamic efficiency case when the resource is scarce. And let's go ahead and do that. I see from my notes that I have the algebra but not the graph, but I've distributed the graph widely and it's on our website, the Moodle site. All right, let's get started. Here's just a reproduction of the slide from class of the first scarce resource problem we did. And they all pretty much look the same. Notice, let me go to the pointer here. Notice a few things. This is our two-period model. The demand in each period is the same at P equals 500 minus 0.5 Q. That's the willingness to pay. Marginal costs are constant at $100 per kilogram, and discount rate is 5%. So that's the case we're doing. Oh, we need one more piece of information. There are 1,000 kilograms of diamonds in existence. So onward we go. To solve these problems, well, let's first write down the key information that demand in each, I need to go back to the pen. Demand in each period, that's a D, believe it or not, is P equals 500 minus Q. And that's Q1 and Q2. It's the either period. We have the same demand. Marginal cost in each period is, actually, marginal cost is constant at 100 in period 1 and in period 2. The discount rate for getting period 2 values into period 1 present values is 5%. And the total resource available is 1,000 kilos. And that's going to be a pretty important part of our solution. So the first thing you do to solve these problems is check for abundance or scarcity. You got to know which case you're working with because the analysis is different depending on what you've got in front of you. So to check for abundance, you just map out the supply and demand. You don't have to do any present value of marginal net benefit analysis to do that. So we've got this demand curve that's got intercepts at 500 and 1,000. P equals 500 minus Q over 2. Oh, I miswrote that. It's 500 minus 0.5 Q, which is Q over 2. Sorry about that. Marginal cost constant at 100. And lo and behold, we find that that's 1,000. We find that the quantity demanded, the equilibrium quantity bought and sold is 800 in each period. That's what the market would do in absence of any marginal user cost signaling scarcity. So that's 800 plus 800, 2 times 800 is 1,600, and 1,600 is greater than our 1,000 available, so we know we've got scarcity. So had it been less, 500 or less in each period, we would have had an abundance, and we wouldn't have had to do what comes next. All right, what comes next? We've got the scarce resource case, so we've got to, we know that we've got to get marginal net benefit functions. And it turns out marginal net benefit function undiscounted in period 1 is equal to the undiscounted marginal net benefit function in period 2. And that's just the difference between the willingness to pay function, got it right this time, and the marginal cost. And that just gets us to 400 minus 0.5 Q. And that's good in period 1. Marginal net benefit in period 1 is 400 minus 0.5 Q1. Marginal benefit in period 2, undiscounted, is 400 minus 0.5 Q2. But our condition for dynamic efficiency requires us, let me just write that down. Efficiency requires the condition that the marginal net benefit in period 1, which is in period 1 present value terms, that has to be equal to the present value of the marginal net benefit function in period 2. That's our dynamic efficiency condition. And so that translates into the following: 400, the marginal net benefit function in period 1, is going to have to equal the discounted marginal net benefit in period 2. So that's 400 divided by 1.05, because 5% is our discount rate, minus 0.5 divided by 1.05. We're just dividing all that marginal net benefit function by 1.05. That's Q2. And just to make that look a little bit better, 400 minus 0.5 Q1 equals, getting my calculator out, and by the way, I found out what my error was in that long calculation of surplus. 400 divided by 1.05 is 380.952. I just couldn't read my own writing, so I read my own 0.95 as a 0.93. Duh. Anyway, even at my age and experience, I'm capable of making just as stupid an error as anybody else. That's equal to 0.476 times Q2. All right, well, as I've talked to many of you, looking over your work, but also to the class, we've got one equation and two unknowns, and we can't really solve that. We can't solve that for any unique value. We need to know something else. Fortunately, we also know something else. We also know that Q1 plus Q2 has to be equal to 1,000. I would say less than or equal to, but we've already verified that this is the scarce case, so we're going to use it all. And what that's going to let me do is to put Q1 into terms of Q2. Q1 is going to equal 1,000 minus Q2. Well, now I can somewhat easily get to one equation and one unknown and bring this home. So I'm going to substitute this animal, Q1 equals 1,000 minus Q2, in for Q1 here, and then I'll end up with one equation in terms of Q2, and I can solve for Q2. All right, so where do I go? 400 minus 0.5 times 1,000 minus Q2 equals 380 minus 380.952 minus 0.476 Q2. Now it's just algebra. Watch this sign error here. I warned you about that in class, but I have seen that sign error, this sign error, so often in my 22 years teaching at Pacific in this class and others. So be careful of that. This is equal to 400 minus 0.5 times 1,000, that's 500, plus 0.5 Q2. That plus comes because this is negative 0.5, and I'm multiplying through by negative Q2. Negative times the negative, negative 1 over here, times negative 1 is positive 1. So we end up with positive 0.5 Q2. All right, and that is what's equal to 380. That's supposed to be a 0. That, even for me, is looking pretty ugly. I never was known for my penmanship. 380.952. It's somewhat frightening to think of what I was known for. Anyway, minus 0.476 Q2. Let's add 0.476 Q2 and add 100, right? 400 minus 500 is just negative 100. So if I add 100 to both sides, I'll get rid of that. And I end up with 0.976 Q2 excuse me, equals 400 480.952, and it turns out that Q2 is equal to 480.952 divided by 0.976. That turns out to be, let me look at my notes, 492.779. I took everything out to 3 digits because I decided I was going to go back and really figure out what was my error, and lo and behold, it popped right out at me once I did this exercise right at this step here. All right, and then since I know that Q1 is 1,000 minus that amount, so it's 507.221. That's the problem. Oh, I guess I should talk about how to get the marginal user cost. That's not too hard to do. Let me add a page to this screencast. To get the marginal user cost, MC sub user is the way I'll call that. Remember that that's the equal to the marginal net benefit, or the present value of the marginal net benefit in period 2 is the opportunity cost of taking 1 kilo of diamond away from residents that are going to live in the next period. And that would be the value of that last kilo to the residents in the next period. Marginal user cost, we can get it by plugging the dynamically efficient quantity into either marginal net benefit function. It's just slightly easier to plug it into the first one, and so that was 400. The period 1 marginal net benefit function is 400 minus 0.5 times, what was the optimal quantity? 507.221. I didn't do that step ahead of time, so pardon me while I fumble around with my calculator. 400 minus 0.5 times 507.221 is equal to 146.3895, bringing it out to 4-digit. And so by the way, the price in period 1 would then be equal to the marginal cost of 100 plus that marginal user cost, that's the scarcity signal, 246.3895. So this was just the marginal user cost alone, so the price would reflect the marginal user cost and the extraction cost of 100. That's where that comes from.